Welcome back to another edition of the Quantum Yoga Podcast. We're here with Dr. Rollin McCraty physically at the HeartMath Institute Research Facility. Thank you for inviting me onto the campus and for taking your time to speak with us.
Well, Jonathan, I'm happy to do it.
Just give us a background real quick. How did HeartMath get started, and how did you get linked in with HeartMath?
Oh, well, let's see if I can make a long story short there. I mean, really, HeartMath was really founded by Doc Childry, and it was through my meeting him and most of the original group that helped Doc found HeartMath through our various walks of life that we met him and come together to do this. And some of us, actually, long story short, I ended up in Boulder Creek, in the 70s, late 70s, for other reasons. I was one of the first consciousness degree granting institutions that actually had accredited studies in consciousness studies. First, I think one of the first ever was here in Boulder Creek. So that drew me to Boulder Creek. And then I had moved to Southern California to start one of my companies that I had started. And so anyway, ended up back here. So I had the right place all along, just I had to get sidetracked before coming back.
Yeah, well, it sounds like a perfect synergy. You end up landing here. I would love to just jump right into some of the science here. Talk to us about the nervous system of the heart, the neurocardiology, and how this relates and communicates with the brain.
Okay, sure. You kind of already said it in a way. There is a relatively new field, 20, 30 years now, called neurocardiology. And these are typically cardiologists that also have neurology backgrounds, because what you're typically studying here is quite literally what's technically called the intrinsic cardiac nervous system. And the name has been nicknamed for that as the heart brain. That's not from me, that is from the neurocardiology community. And this neural system within the heart is quite complex. It's ganglia, and ganglia just means a group of neurons, and there's pictures of them we can show people and stuff which I've gotten from my friends in neurocardiology. But a ganglia just means a group of neurons that are wired together in a functional way that are outside of the brain. So there are many ganglia throughout the body, but within the heart, there are many ganglia that are all interconnected, and that's what gives rise to this functional brain. So the neurons that are within these intrinsic ganglia within the heart, or the intrinsic cardiac nervous system, have all the same functions as the neurons in our head. They have been proven now, it's not a hypothesis, that they have short-term memory, long-term memory, neurogenesis, neuroplasticity, all these functions. And in hindsight, we probably should have known this all along, because the heart really has to have its own intrinsic nervous system to function the way it does, to have rapid decisions made at the level of the heart. And then, in fact, just a point here is the most of the textbooks, if not all of them, that are still being used are wrong. For example, they show the neural connections between the heart and the brain, which there's two primary pathways that we typically think of, the sympathetic and parasympathetic nervous systems. And what we have to realize, though, is in both branches of the autonomic system, sympathetic and parasympathetic, there are both what are called afferent and afferent neural pathways. Afferent just means, in this context, going from the heart to the brain, efferent from the brain to the heart. So both the spinal tract pathways, which is typically the sympathetic chain, and the vagus nerve, which is the parasympathetic, are made up of both efferent and afferent. In the vagal side especially, it's the one that has the most ratio from heart to brain, or body in general. In fact, for conservative, it's estimated that, this is the conservative estimate, is that 80% of all the neural fibers in the vagus nerves, there's two of them, one on each side of the body coming down through the front of our body, are afferent. Most estimated at 90%. So at best, in other words, 10% of those neural fibers, and there's thousands of neural fibers in each one of the two vagus nerves. They're big nerves. So probably at best 10% is brain down. And the majority of the afferent, of the 80 to 90%, are from the heart and cardiovascular system. So my point to circle back around to where I started this, most of the textbooks show the efferent down from the brain going directly to the SA node in the heart or the cardiac tissues and so on, and the same from the sympathetic efferents. It's completely wrong. Not a single one of them goes directly to the cardiac tissues or the SA node or AV node and so on. They all connect into the intrinsic cardiac nervous system. And then within the heart, independent of what we would technically call the intrinsic cardiac nervous system or the heart brain, are about 40,000 sensory neurons. So these are neurons that are tuned to sensing things: pressure, rate, rhythm, hormones. 80% of those are detecting biochemistry. But then you've also got what used to be called baroreceptors, which are sensory neurons that are sensitive to pressure. So you know how hard the heart's contracting, what the blood pressure within the heart chambers and so on are. So all those are all feeding their information into the intrinsic cardiac nervous system, where it's integrated with the information coming down from the brain, so to speak. The brain says we need more heart rate, we got to go chase down a rabbit or something or whatever. Yeah. So this kind of then explains, to give a little fuller answer to your question, observations that really started the pendulum swinging from the old paradigm into the new one, that were back in the late 60s, early 70s. And at that time, to help the listeners understand, the autonomic nervous system was to be kind of considered this rather dumb system that was really there for the brain to tell the body what to do. And of course, nobody believes that anymore, by the way. But at that time, that was the paradigm. And the observations that really started this whole paradigm shift were looking at the heart. When you would see clear indications and measures that, say, the sympathetic system was increasing its traffic down to the body. So we expected you to sweat more, heart rate to go up, all these things that are associated with that. But instead, heart rate would decrease. Or vice versa. You could have vagal influences that said heart should be decreasing, but it would increase. In fact, it's really fascinating to read through the literature, scientific literature of that time, because they were starting to talk about the heart as though it had a mind of its own. And well, we now know it does, but they didn't know that then. So that's really what started much more depth of understanding this. We now know the autonomic nervous system is very differentiated. It's very specific controls and much more complex than what was thought at that time. But that's a little bit of a sidetrack in that now let's talk about the afferent side of this, because we've got all these neural systems coming up from the intrinsic cardiac nervous system to the brain. And around the same time period that I was referring to, once they realized the heart was acting like it had its own mind and was overriding the directions from the brain and so on, that's what started the in-depth look into this heart-brain connection stuff. And shortly following that, it became clear that these neural signals from the heart to the brain have profound influences on brain function. And in fact, in many cases, although they tried to kind of hide it, but it's pretty clear in the older literature, the heart was changing before the brain to actually help prepare the brain for what was coming next. And this led to a whole kind of new understanding. And so neurocardiology has been an important part of mapping out all these neural connections and the pathways and within the heart and between the heart and the brain. And it's really the psychophysiology community that's looked more at how these afferent neural signals from the heart affect perception and brain function and our capacity to self-regulate, but quite literally have a very large role in informing the brain to what we actually feel, what the body's feeling, especially the heart. So we now have, I think, better understandings of why we have so many sayings in our language. Like, well, hopefully, I don't know if you're married or not, Jonathan, but hopefully you did not tell your wife, "I love you with all my brain," right? So, but it's in our language, right? We always talk about, "God, I love you with all my heart," or "Play with heart," right? Or "Go to your heart; it knows the answer." I mean, just all these sayings that are in our language that we've intuitively understood and known. We now are really trying to understand. We're not trying, or starting to understand the neurophysiology of and the way we're really wired.
When my entry initially into understanding the ANS was through like adrenal fatigue. years ago. And so many people were back then, I guess, were being told, adrenal fatigue, this is your issue. And so then you get, from there, you kind of start to get into connecting to sympathetic nervous system, parasympathetic nervous system. I know they're not directly the same thing,
Not at all. Yeah.
but there is this, how do I put this? It's just very muddy. It seems very muddy when you start to go online as a biohacker or self-initiating health to kind of understand what all of these things mean. And one of what you're pointing to with these afferent signals in the vagal system is
and not just vagal. Remember, there's both. You have afferents on both sides.
Yes.
Right? So, in fact, if I may, I don't want to cut you off. A lot of people are hyper focused on the vagus, like it's everything, and forgetting that that's only half of the autonomic nervous system. So the sympathetic has afferents as well.
Okay.
And efferents. But anyway, I don't want to.
Yes. Let's go there, because you mentioned to me in one of our earlier conversations that it's not that people's, generally speaking, people who are stressed, it's not that they have a lack of parasympathetic tone or vagal tone. It's that there's an underfunctioning of.
Okay.
Do you get where
I think I get where you're going.
Yeah.
So let's go back to adrenal fatigue.
Yes.
First to start with, because that's a concept that's pretty widely used in some of the naturopathic sciences and so on, and that's fine. I personally think it's more of a metaphor, because when we're talking the adrenal glands, we're talking the hormonal system, which has nothing to do. Well, it interfaces with, but it's a completely different system and axis than the nervous system. And the idea there is that the adrenals can't produce cortisol and so on anymore. And actually, one of my friends who invented the adrenal stress index, in fact, was the first to create it, that idea, who's done hundreds of thousands of assessments of adrenal function at the hormonal level, and says it's very rare that you actually have somebody with true adrenal fatigue, that the gland can't produce hormones. Yes, there's shifts in ratios and under functioning, but it's not quite like we think. But that's independent of the nervous system, and I could go into a whole thing there, but I'm going to avoid that right now. Anyway, so when we look at the function of the nervous system, it can certainly be under functioning, both branches, and we tend to pick on the vagus a little bit more than the sympathetic inappropriately, is what we find. 'Cause we just to give reference here, we do one of the things we do in our lab is we do 24-hour heart rate variability assessments for clinics all around the world. So we've got data from all over the many types of populations from around the world over many years. And what really happens usually through long-term stress, chronic stress, or you have a traumatic event, something that really hammers the system, it's the sympathetic system that's underperforming usually. So there's this idea that's very rampant, where the sympathetic is considered this bad guy part of the nervous system. It's overactive, because we're stressed. And yes, when we have to meet a challenge, right? You want a healthy sympathetic system. There's a lot of, I got to go climb the stairs to get to my office. I want a healthy sympathetic system.
So that would be the example where the sympathetic's not stepping up to the task being asked.
Well, if it's under functioning, but the idea that dominates a lot of the medical literature still to this day is this idea of metaphorically we could say a stuck gas pedal. So we have this overactive sympathetic system that's driving everything into hyperactivity. Adrenal fatigue is the metaphor used for that, and so on. What we see in reality is that far more people with long-term or chronic stress have poor functioning sympathetic system. It's under-functioning, right? So it's kind of where this is a long-winded answer to your question, but where you're can also have happening is not so much it's the stuck accelerator. We have bad brakes. Right? And in reality, we also see clinically a lot of people that have both under-functioning sympathetic and parasympathetic, and that's a kind of a later stage of exhaustion or whatever you want to call it, or low functional status. So I'm just going to ramble a little bit here, I think, to help answer your question. So there's a lot of focus on the vagus nerve now, and especially in psychology, which is appropriate because it's the vagus that, in general, if we're just talking normal autonomic function, when we increase the outflow from the brain through the vagus to the heart and other systems, it slows heart rate, and that's absolutely true. But if we have bad brakes, we're not able to slow the system down. So it's not necessarily a stuck accelerator. But the reason the vagus is getting a lot of attention is because it's that ability to self-inhibit, to slow heart rate, to inhibit, the heart rate's just reflecting a much broader in self-inhibition that's going on. It really underlies our capacity to self-regulate.
Right. That's what it gets down
to.
So
Impulse control, to be able to socially engage. In fact, it's the brain systems that drive the vagus, and the vagus is really considered the evolutionary, what evolved in humans to be what Steve Porges calls the social engagement system. So it's appropriate to be looking at it, but here's the kicker on this from a health and maybe a biohacking perspective, is we certainly see plenty of cases with low vagal functioning, but I need to back up a little bit here for this to make sense. What I'm talking about here in terms of how we measure this stuff is what's called heart rate variability. And heart rate variability is quite different than heart rate. Heart rate's just how many times did the heart beat in a minute, right? We all know what that is. But in a healthy person, in a resilient person, our heart rate is quite literally changing with every single heartbeat. The time between each pair of heartbeats is always varying. And we have more of this intrinsic natural variability, which is quite literally generated through both branches, efferent and afferent, of both sides of the nervous system. The heart, brain, nervous system all have to be functioning properly to have normal heart rate variability. So on one level, it's really simple. It's looking at the beat-to-beat change. On another level, you can spend an entire career trying to understand this stuff, the heart rate variability, because it's such a deep measure of what's going on inside of our body once it's understood.
Yeah, well, let's take some of these metrics, define them quickly, then head back to that.
That's where I think I'm headed anyway. So I'm not going to get into the metrics, but let's just say that we have more of this natural variability, which we do when we're young, and it gets less as we age. So there's a almost linear relationship between the amount of variability we have in age. So it's one of the best measures we have of physiological aging versus our chronological age. Now, if we have a lot of stress, I'm talking about overall amount of variability now, long-term stress, chronic stress, starting a new business, going through a divorce, whatever, those kinds of, where we're putting out more energy than we're recovering. That leads to lowered variability for our age. And that's important from a health perspective, because that is a stronger predictor of future serious health problems than any other marker I know of. Certainly it's another category past our blood pressure or our cholesterol levels and all these types of things.
So we're talking about RR intervals. We're talking about, okay.
Yeah, they're called, RR intervals is one language. It doesn't have to, RR refers to the electrocardiogram, the R wave, but we can measure HRV from pulse. So it's really, us in the field would call it more what's called the interbeat interval, RIBIs. So it's quite literally the measurement in time, in milliseconds of the time between each consecutive heartbeat.
And that is what you will see change. That is the sort of longevity marker that you look at.
Well, or biological age marker.
Got it.
You want the amount of those IBIs we have overall relative to our age.
Got it.
And if it's lower than it should be for our age, it's not good. Okay. So that's the how much, but this is where it gets a little more complex, because HRV also reflects, we have to look at the pattern of the rhythm as well as how much of it we have. But that's a different kind of path that's important to probably talk about. So the reason I backed up to explain this is if we look at HRV, there's certain, it's a complex waveform, because there's multiple systems within the body that are all contributing to this variability and these rhythms and patterns. One of those reflects vagal function and activity. We can very clearly separate out the effects on heart rate and variability that are because of vagus activity, both efferent and afferent. But if the function's low there on the vagus side, that is not that predictive of future health problems. A lot of people don't understand this. What it is more reflective of is, if it's lower than it should be, is low capacity to self-regulate. So these tend to be the people that have impulse control, anger issues, anxiety, panic, all these things that really reflect our a lowered capacity to be in charge of ourselves, to maintain our composure, to self-regulate, socially engage in a positive way, rather than getting angry and stomping off and all these types of things. Now
So,
it's this.
so this would be high frequency.
Yeah, in
content,
HRV
or-
language, it's the high frequency, or what's called the RMSSD in the time domain, to get into specifics here. But my point is, it's the very low frequency rhythms in the heart rhythm, which is one of the 4 primary bands, that is most predictive of future health problems. Right? So this is not commonly understood, but low VLF function, very low frequency, which is a rhythm, by the way, that is actually generated, we now know, by the intrinsic cardiac nervous system, is the fundamental source of this. That if that rhythm's low, this is the one that's correlated or associated with all-cause mortality, right? And all of the more serious future health risks. Now, I've talked a lot about stress in it, because that's when we see low HRV, any frequency, but especially VLF, that's the one that is more associated with long-term stress. That's why I've talked about it. But it can also be a physical disease process, right? And one of the stronger associations, for example, with lowered HRV, especially VLF, is inflammatory problems, right? So that kind of explains why VLF, HRV in general will drop out or become lower than it should be up to 2 years before the onset of symptoms. And things like in diabetes and metabolic issues, cancer. It's a very wide range now that low HRV precedes. So it's a great overall functional status measure. But if your HRV is low, what it can't tell you is what's going to happen. In other words, if I see somebody with low HRV, which we see a lot of in our work, in the analysis work I was talking about, what I can tell those physicians, what they know is, okay, I get to take a deeper look at this person. We've got to find out what's going on. So you'd want to screen, make sure they don't have an inflammatory issue going on, high inflammation, or diabetic neuropathy types things. And if that's you clear that up, but that's not the issue, then more than likely it's a stress issue.
And this, I think I remember hearing you say that you can only really get this from a 24-hour measurement.
Well, that's not quite true.
Okay.
It is true. By far, in my opinion, and I think most of my colleagues in the field would agree, that a 24-hour assessment is the best way to go. That's kind of the gold standard, because it's called heart rate variability for a reason. It varies. So if you actually look, I see you've got one of our reports here that I'm talking about. If you actually look at the which we plot is the actual HRV, the actual rhythms over the 24 hours, it's varying. You can look at 5 minutes, and it's radically different than another 5-minute segment, and so on. So to really get an overall look, you have to look over 24 hours. Right. And that's one of the problems, by the way, with a lot of these little apps that are out these days that take these short-term snippets. It's telling you nothing about your overall HRV, quite frankly. And there's some, I won't go into that, but now at the same time, back up. There's a lot of other benefits you get out of 24-hour measures. You get to find out what's your overall 24-hour heart rate. That's a really important measure, as it turns out. So the average, national world average, really is 73 beats per minute. We see people routinely these days, and it's increasing as well, what we see in the lab, people 24-hour heart rates of 90, 95. So these are systems that are never able to recover, right? But it's not necessarily because of a stuck bad guy sympathetic system. It can be, that's again where we might have a poor functioning vagal inhibition, right? But you also get to see circadian rhythms and sleep quality and the shifts between REM and normal, slow wave sleep. All that's reflected in the HRV. So we get to see all of that in the 24-hour report. And I know you have a question, but let me just finish this thought. So we spent a couple of years in the lab a few years back developing a short-term protocol that would have reasonable correlations with the 24-hour measures in terms of the overall how much of it we have. And we did come up with that. And it was kind of, we had to laugh at ourselves at the end of it, to be honest. We got into some complex protocols and stuff, but at the end of the day, the end of the period, it was the shortest and simplest of all the protocols. It was the best. You can do it in 1 minute. And in fact, this is a a protocol we now have built in with age norms into one of our devices called the M-Wave Pro Plus, which allows you to do your own HRV assessments. It's really more of a professional device that allows you in 1 minute to get an assessment of your overall HRV. And it's a challenge test. It's where we pace the person's breathing and have them breathe as deeply as they comfortably can, which is really important that you do both those things. Because if you breathe at the resonant frequency of the cardiovascular system, which is 0.1 hertz or a 10-second rhythm, and breathe as deeply as you can comfortably, that is asking the question, what is the maximum HRV your nervous system can produce at this time? And that has almost a 0.8 correlation to 24-hour measures of the how much question of HRV. So it's a great short-term assessment. So what we recommend to clinics is this is something you can do with every patient. It takes 1 minute, right? Or people can do it themselves. And it's a far better way, in my opinion, measure than these resting state things that you do that because it's a challenge test.
Like first thing in the morning?
Yeah, well, if you're going to do a resting state, like if you're looking at overtraining or the types of things these apps are for, yes, you absolutely want to do it at the same time of day. That helps with some of this variability issues, but it's still not, the best way necessarily to go. There's nothing wrong with that, as long as one understands the context and what they're really looking at. But anyway, if you flag low on this 1 minute deep breathing test, then we always recommend you follow that up with a 24-hour assessment so we can really see, okay, what's really going on here and what might be the deeper issues that can help sort out.
You were talking about these self-regulatory capacity metrics like high frequency and RMSSD, then you got into VLF. And I would like you to clarify and talk a little bit about low frequency, because this is generally termed as, this is the sympathetic domain.
Oh, it's utter nonsense. So for listeners here to understand, when we look at heart rate variability, it's a complex waveform that, as I mentioned earlier, has multiple physiological underpinnings that create various rhythms. So one of those rhythms that's reflected in heart rate is our breathing rhythm, and that's the one that's mediated by the vagus nerve. And that is the higher frequency changes, the more rapid changes in heart rate. That's why it's called high frequency from a power spectrum analysis perspective. So if we take, usually a typical window would be 5 minutes, but it could be any and do a spectrum of it, you're going to see multiple peaks. So the one that we deem high frequency is your breathing frequency. And that's the mechanism of that is that you also have stretch, we'll call them, to keep it simple, but sensory neurons in the lungs that are stretch sensitive. So when we breathe in, those neurons are activated because we've stretched the lungs, and they flow up to the medulla, and they basically inhibit the outflow of parasympathetic, efferent parasympathetic activity to the heart. Heart rate increases. Breathe out, those neurons are released. Okay, parasympathetic activity resumes, heart rate slows. So our breathing rhythm is always modulating the heart rhythm. Now, it's crazy what's going on out there in the literature. So you see papers now that talk about it. All HRV is all high frequency, it's all parasympathetic, it's all breathing. Utter nonsense. 30 to 40% at most of our overall HRV is produced by the high frequency rhythm, the breathing rhythm. So anyway, that's our, if done properly, you can use that as a measure of vagal function. So high frequency is the power spectral language for doing that. Then the next peak that you typically see, even if somebody's asleep, right, is called low frequency. And the mechanism for that is it's called the baroreflex in the older literature, but it's basically the neural connections between heart and brain that are involved in short-term blood pressure regulation. So it's always there, and this is why when you stand up, you don't pass out, because heart rate and the blood pressure has to rapidly change within a heartbeat or two. Otherwise, you'd pass out, right? From sitting down to standing up, you have to have rapid adjustments of blood pressure. So that's this mechanism, and that rhythm is reflected in the low frequency region of the spectrum. Okay, then you've got the VLF rhythm, which is a slower rhythm than that, and the center of the VLF region is about a 10-second rhythm. By the way, the center of the VLF is about a 90-second rhythm, and then you get ULF rhythms and stuff below that, which we won't go into. So the way that these frequency bands, as they're called, were created. Is you put lines between these natural peaks that always appear in the HRV because due to these underlying mechanisms. And these were friends of mine that did this way back in a long time ago. And we've been doing this before it was called heart rate variability. In fact, one of our scientific advisory board members, a guy named Don Singer, who unfortunately passed away a couple of years ago, is the man credited for the first to use the term heart rate variability. So he's the guy who got credited. He was a great one of my mentors. And so it was Don and a couple of his colleagues that created these frequency bands. And the way they did it, he's funny, he was quite a character. Yeah, the way we did it, so these are recordings from 24-hour recordings, mostly from sick patients, by the way. And you look at these spectrums, from lots of patients. You see, there's a peak that tends to be here. We call that high frequency. There's a peak that tends to be here and a peak that tends to be here. All right, well, let's just kind of get between them and we'll stick lines in there, and that's the frequency bands. That's literally how it was done. Okay? So in an ambulatory context, it appeared, and there actually is truth to this, that the low frequency rhythm increases. That peak, you get more power or more rhythmic activity in that low frequency bandwidth when people are active. They're doing things, which is activating your sympathetic system. So this low frequency peak must have something to do with sympathetic function. It was a reasonable assumption. And there's actually some truth to it. In an ambulatory 24-hour measure, you're climbing stairs, doing things, talking, walking, right? All the things that are naturally activating sympathetic system. Okay, fast forward a few years, people started doing resting state recordings, like we're sitting here at the table, and even the 1-minute test I was saying about, these are all resting state assessments. Or we're wanting to do HRV biofeedback, right? Usually where you're setting and you're trying to do something. So where the problem came in here was the assumption was made that the interpretations are the same as when they're ambulatory. They're not. So we're sitting here now. Is there any major sympathetic activations going on?
Right.
No, unless we do some major stress protocol or something to really cause that. And even if we did, we now know it has absolutely nothing to do with the LF band. So those, as I mentioned, those lines, those cutoff points between band regions were arbitrary. They're stuck in there. Our physiology doesn't know that and doesn't care. Right. So in reality, what happens when you do activate a sympathetic system is we have the VLF band I was talking about. It's generated by the heart. It's a really important band. We always want it to be there. But when we do modulate the rhythm of that band through sympathetic activations, it will change its frequency and its amplitude. So it moves up and dumps power in spectral language into the LF band. But the actual mechanism that produces the pure LF band has nothing to do with the sympathetic nervous system. Right? So then there came this idea of the LF-HF ratio measuring sympathetic and parasympathetic balance. Right? Utter nonsense, if you get where I'm going with this.
Yeah, absolutely. Well, it's what I'm getting is this is vastly complex, and that many of these apps that are being used to measure HRV, they're taking like one of these metrics, and now this is the state of your this is the state of your health,
which is of course nonsense as well. And a lot of them aren't even the ones that reflect future health that are being reflected in these things. People, they read a paper and think they're experts. And it's taken a long time for us to come to these understandings. And of course, we've been part of sorting all this out, so I'm more steeped in it than most would be. But where the literature has really gone wrong in resting state recordings, this idea of the LF-HF being anything to do with parasympathetic balance is just wrong. And unfortunately, that's in a few papers. People read that and think they don't know enough to really dig in deep enough. And there's a lot of authors, myself included, that have been pointing this out, and that's starting to change now. Fortunately, I can review a lot of papers and get to point out, when they do that they need to. Yeah. And it's really too bad, because I can't tell you how many papers are in the literature where they do some type of intervention, whatever it is, whether it's rest and recovery interventions, acupuncture, whatever. HRV biofeedback in the old days, and they see this beautiful increase in LF function. Absolutely what you'd want to see. You've enhanced vagal function, because the LF is all vaguely mediated, by the way, those neural pathways. Both LF and HF are all vaguely mediated. And they've had a wonderful finding. And then they spend their whole discussion trying to argue themselves out of what they've just shown because of this misinterpretation that they increased LF and it was just sympathetic activation, this bad guy sympathetic. It's just too bad of what's gone on there.
Wow. Let's talk about emotions.
Sure.
And how that affects aspects of HRV. And I think it'd also be prudent to somehow weave in your idea of coherence and how you even measure that.
Right. Now we get into I think actually a more interesting thing. So everything we've been talking about so far is how much of this HRV do we have? So independent of how much of it we have, in other words, we could be a young person and a lot of it, and an older person, an old fart like me with less of it. There's another deeper level that's reflected in the HRV than the how much, and that's the pattern of the rhythm that's produced. And it's important for people to understand when I say rhythm, if there wasn't beat-to-beat change in heart rate, right? If you actually plot that at how it looks, the HRV, you see this kind of varying patterned rhythm, right? But if the time between each pair of heartbeats is the same, you have a flat line. There is no heart rhythm. The heart becomes like a metronome, which is, again, the last thing you want to have happen. That's what's associated with sudden death and all kinds of not good things, right? So there's the how much, but even more fundamental, more where information is reflected about what's going on internally in the activity in our nervous system, actually within the brain, is the pattern of the rhythm. Now, these are where it becomes state-specific, independent of how much. So if I get angry, for example, or frustrated, you ask me a question I don't like and I get mad at you or something, not that you're going to do that, what we would see is that the pattern of the rhythm, and you'd have more variability than I do because I know I'm a lot older than you, but so even though you might have a bigger range of variability, our patterns, if we got angry at each other, would both start looking very chaotic, which quite literally is reflecting a lack of harmony within our internal systems. Higher level brain systems, which are then reflected in the autonomic system, the activity, the coordinated action between sympathetic and parasympathetic, and a bunch of other stuff. So this goes back to our work in the early 90s, where we were the first to really even be looking at HRV in this context. And back then we were doing all the stuff with three-letter acronyms, EEGs and EMGs and ECGs and all that stuff, and looking at different emotional states. And I think we were kind of early in the game of investigating positive emotions. At that time, I think there were like 3 papers in the literature on positive emotions. I mean, it was sparse. That's radically changed since then. But anyway, consistently, it was the pattern in the heart rhythms that best reflected emotional state. Right. So, in general, we can say now that what we tend to call depleting emotions. I'm not trying to put value judgments, but when we get angry, frustrated, anxious, it creates a disordered heart rhythm pattern. And when we feel good, things like appreciation or kindness, got a good deal at the mall, you just feel good, right? Our heart rhythm goes into a completely different pattern that we call coherence. It's sort of the sine wave looking pattern I see on you did good there on your graph I see of yours.
Working on it.
Yeah. So about 300 studies later, now there's been, we just crossed the 300 mark of mostly independent studies who have verified this and used various aspects of our technologies and training methodologies and research. Pretty clear that when our body's in this coherent state, which is really reflecting harmony between heart, brain, and all the different systems within the body, a lot has to go on internally to get that nice little coherent rhythm in the heart because of all these internal systems that have to be working together in a coordinated and harmonious way. That this is the optimal state. It's the optimal state for facilitating the body's natural regenerative processes, right? Hormonal balance, immune system function, but especially cognitive function. Because I mentioned earlier how all these afferent signals from the heart go up to the brain and have profound on brain function. So when we're in that, what we now call incoherent heart rhythm state, that quite literally inhibits the frontal cortex from operating well. That's why when we get mad, we can say or do something really stupid, right, that we would not otherwise do. Our frontal cortex is taken offline. The ability to discriminate appropriate behavior, abstract thinking, and so on. On the other hand, when we're in a coherent rhythm, it facilitates those same functions beyond and above our normal walking around state. So we're able to make better choices, better decisions. And physiologically, a lot of benefits. Our blood pressure is going down. Heart's doing less, is getting more done with less work. For example, ejection fraction increases, a bunch of different very beneficial measures of inner efficiency and harmony. And it's emotion-driven.
Well, it's amazing to me when I just tell people how intricately involved emotions are in the physiological state.
They run the show. It's really easy. You can do this with one of our inexpensive devices, or we've done it for years. We tend to think about thoughts run the show, right? They don't. Can have you wired up to EEGs and all the stuff, and have you count backwards, serial subtractions, and all these so on things. Not much happens in your physiology. Your heart rate doesn't change. The patterns in your EEG might change a little bit here and there, and your rhythms, not much. But once you trigger an emotion, if you get frustrated because you're having to do serial subtractions, you're starting to get embarrassed by it because you're not doing well, or you start to get frustrated by the process, a lot of physiological changes happen rapidly and big. That's when you see the changes in the nervous system, the hormones, all of that. So emotions really do run the show. And that's a whole other topic, maybe another interview someday. We can talk about the emotional physiology and what's really going on and how that really works. But so you asked about magnetic fields, right? So when we measure, a doctor or whoever measures the electrocardiogram, what you're doing is you're sticking electrodes across the chest, or same thing with brain waves. You put electrodes on the head. You're measuring current flow. That's what they measure. It's why it's called the electrocardiogram. We're measuring the electrical current flows. In basic physics, we know that whenever you have a flow of current, you create a magnetic field, right? I mean, you can't separate those two. So when we talk about the heart's magnetic field, I am talking about a very classical, traditional magnetic field. Now, the electrocardiogram doesn't see the magnetic component. It's only measuring current flow. To measure the magnetic field, you use a different instrument, a magnetometer. So it's really interesting. I've actually heard doctors, there's no such thing as a magnetic field of the heart. Well, that's silly. We measure it, in fact, with a magnetometer. With today's equipment, you can measure the magnetic field from every heartbeat about 3 feet from the body. Just for reference, you can take the same instrument at the same setting, you lose sensitivity about an inch away from the head to measure a brainwave. I mean, it's crazy that people don't think this is true. Almost every teaching hospital has equipment to do this. They do it routinely, right? It's called MCG, the magnetocardiogram, or same for brain, right? They're called MEGs in that case. And it's done clinically every day. Right now it's going on probably hundreds of places right here in the United States that these are being measured for specific clinical reasons. So we know that the heart's radiating a magnetic field. We can measure it. And we, just quite a few years back as well in our research path, we started doing, I'm an ex-communication engineer, just worked for Motorola. So I know a little bit about spectral analysis and modulations and how magnetic fields carry information like our cell phones do every day. Right? I mean, how does our signal get from the cell phone to the cell tower? It's a electromagnetic field that's carrying that signal. And the reason our phones work indoors is because of the magnetic component. They go through things, right? So if anybody doesn't believe magnetic fields penetrate things, well, stop using your cell phone indoors because it's impossible. You get the humor there, right? Yeah. So the same thing for the magnetic field of the heart. It goes right through the tissues, radiates out into space around us, and can be detected with these magnetometers. But when we decode that information through spectral techniques, can quite clearly see that emotional state information is riding on those fields. Very analogous to how our cell phone is carrying the photograph of the cell or your phone conversation, by those same magnetic fields. Same way. And then the next step, which was amazingly easy to do in hindsight, was to show that not only are we radiating these magnetic fields, which are clearly carrying information, we can decode it. We can nowadays measure the magnetic field, decode that information, and tell with about 75% accuracy somebody's emotional state, just by looking at the spectral patterns. So the next step, though, was to ask the question, okay, we know we're broadcasting it. Are we also receiving it? And that was a relatively easy answer to get. What we see is that our nervous systems are exquisitely tuned to the biologically generated fields that we produce. So in other words, we're sitting here across the table within each other's cardiac field, and there is a literal, measurable transfer of information going on via the magnetic field domain. You can measure it. So in other words, we could see synchronization going on between us and information exchange and so on.
Can you change that field size?
Well, not size. So the size of the field. So the field is generated by the beating heart. It's the current flows in all the cells in the heart combining as the heart contracts at the same time. So the size of it, well, if the heart contracts stronger and harder, yes. But the more relevant question I think you're getting at is, can we change the information being carried by the field? Right?
Yeah.
Right. So, and does that affect other people? And no question, the answer is yes to that. I mean, there's where sayings in our language come from, and back to that. The tension was so thick you could cut it with a knife, right? Or, God, back in the 60s, God, do you feel the vibes in the room, right? I mean, we have these sayings because there's a reason. They're real. Yeah. We're just able to measure them now. So a couple studies have been done, pretty well done studies actually, that show, for example, if I'm in a coherent state, in a heart rhythm coherent state, there's a mathematical association between the rhythm and the information carried with the field, by the way, that can actually help lift those around us into a more coherent state, even if they don't know we're doing it. In other words, if one of us was getting coherent here, that's really going to help lift the other person into a more balanced and coherent state.
Can you apply this, the fact that this field is all pervasive in our cells of our body,
sure,
that it's having epigenetic effects? And
not yet. To actually prove that, it's certainly my belief and hypothesis. I mean, the whole epigenetic side of things, I just love what's going on there in epigenetics. I talk about a paradigm shifting, disruptive to some very long and cherished theories that's going on. And there's a lot of great work in epigenetics. And so, I mean, we now know that there's the biochemical pathway. We get stressed, for example, that creates, cortisol and other hormones that through signaling processes to the cell modulate the expression of the DNA, as opposed to other categories of hormones that don't do that. And enough patterns of that, you can lead to epigenetic changes. But what you're really asking about, and there's some studies are actually starting to indicate that there's a much more rapid, I'll call it energetic communication, which is really what I think you're asking me about, the magnetic field level. So one of my friends, close friends actually and colleagues, is a cardiologist and also a stem cell engineer, a molecular biologist, is doing work and actually publishing his work in journals like Nature. I mean, he's a high-level guy. He's actually literally programming stem cells to be, a neural cell, a skin cell, a heart cell, whatever, through magnetic fields. I mean, that's going on right now, right? So the idea you're bringing up is not far-fetched. So I think it's just a matter of time until we start to understand that every emotion we feel is affecting and programming the expression of our DNA. And done long enough, it creates what I would call a new baseline, where it really becomes an epigenetic or a permanent change that's passed on to the offspring.
And so this would naturally lead to looking at or we'll say natural electromagnetic signals outside of our body in our relationship to them, like the Earth's geomagnetic field, which is a lot of relatively recent work.
So right. So just to reiterate a point I made, what we see in our work is that what our bodies respond to in terms of magnetic fields is those that are in the right intensity and windows of frequency and so on that match what we produce. right? In other words, we're a built-in system. And it makes sense, too. 'Cause if you think of back to my cell phone analogy, sitting here now in this room where there's probably, well, we're out in the country, maybe 50 cell phone conversations going on right now in the magnetic space around us. How do I get the one I want? You have to quite literally create a resonant loop with the frequency you want in your receiver or transmitter, right? Or receiver, and then you instantly transfer energy and information because you're resonant. You're at the same frequency in the right windows of frequency and amplitude and so on. We work the same way. What I'm suggesting here is from our perspective. Now, in terms of Earth, a lot of people know about what are called Schumann resonances, right? Which, they were first mathematically predicted in the 1950s. Otto Schumann, they're named after, but it was quickly recognized when they were first measured in really just early 60s in a way that was kind of meaningful, that the frequency of the Schumanns overlapped human brainwaves. A lot of confusion going on here and a bunch of crazy stuff on the internet about Schumann resonances changing. It's all utter nonsense. There's 8 Schumann resonances, not one. Always has been from when they were first measured. They're the same as they are now. I mean, we have a world network measuring these things, so I can say this with some confidence. The Schumann resonant frequencies are not increasing. They're the same as they were when they were first measured in 1960. Thank God. It would be a really bad thing for us humans if they were changing. But anyway, that's a bit of a sidetrack, but that might mean something to some people out there.
Well, I've asked a few guests about this, and so if you wouldn't mind, just you feel free to go into that a little bit more.
Well, actually, I can, but Schumann's aren't the most important thing. That's why. But they are important because they do overlap EEG frequencies, brainwave frequencies. So basically what the Schumann resonances are, they are the magnetic waves that are trapped between the surface of the Earth and the bottom of the ionosphere. So keep things simple. The ionosphere, which is a plasma, fourth state of matter, acts like a mirror to magnetic waves. That's how ham radio operators work, right? You send your radio signal up and it hits the ionosphere, bounces off, and you talk to somebody from the United States in Europe or China or something, and if you're lucky, you get a second bounce and you're talking to people in Australia or South Africa or something, right? I mean, that's been known for a long, long time. So the magnetic rhythms that have a harmonic, that their wavelength has a harmonic relationship with the cavity, or what the Schumann resonances are. They become amplified and become globally propagating standing waves. That just means they're everywhere all the time, right? And there's 8 of them, right? The 7.8 hertz is the first one, 7.83 for specific.
You guys measure these?
We have because it's part of what's called the Global Coherence Project, our initiative. And so we've had to do this ourselves. Wish we didn't. It's very time-consuming and expensive, but specifically designed magnetometers to measure Earth's magnetic rhythms around the Earth. So we've got sites all over the place. We've got one here, California, Lithuania, New Zealand, South Africa, Saudi Arabia, Colombia is coming next. But so we have the only time-synchronized global network that I know of in the world to measure these things. And there are lots of magnetometers out there, by the way, but they're not designed to measure the resonant frequencies of the Earth. They're looking at the DC field strength and field disturbance, so we can protect satellites and stuff. But they don't see what we do. We're looking at what's called the time-varying magnetic field, the oscillating part. So anyway, there's my comment there. I probably went on a tangent. There's been 2 rounds of it now. This internet stuff about the Schumann resonances are increasing. First time ever we see 30 hertz. Well, utter nonsense. They just had a low sensitivity magnetometer, and there was enough of a rhythm that popped up, but it's the third harmonic. It's always been there. Anyway, enough said there. So the Schumann resonances do overlap the human brainwave frequencies. All 8 of them overlap human brainwave frequencies, in fact. But it's actually a very tiny, well, I shouldn't say it that way. Relative to the more important rhythm that what we're seeing, it's tiny, but still physiologically important. And I'm not trying to just. These are called Fieldline resonances, the more powerful rhythms and Earth frequencies. And so, if you remember back most of us in science class back in, I don't know, junior high, something like that, I think, for me, we got to dump iron filings on a glass plate, and you put a magnet under it. You kind of tap it a little bit, and sort of magically all the iron filings move, and they they outline the shape of the magnetic field. Right? You can move the magnet around. It's fun to play with for a while, and see it move. But they line up in lines, right? Those iron filings. They weren't a homogeneous black blob. They lined up in very specific field lines. Right? Those are called flux lines, in some circles field lines. So the geomagnetic field of the Earth, which is a static field, just like our magnet we put under the glass. In other words, it's a pure magnetic field. It's always there, right? And from Earth's perspective, from a human perspective, the strength of the geomagnetic field, which has the north and south poles, what our compasses tune into, isn't changing. I mean, yes, it changes, but it's over hundreds and thousands of years. So I don't wake up in the morning going, oh my God, it's the strength of the field changing. It's not. But what is very relevant here is these field lines, if you think of them like guitar strings, which is how you should think of them, because this is exactly how they're acting. When you pluck a guitar string, it vibrates, right? And it has a resonant frequency. The note, you change the tension of the string, it changes the frequency. So the field lines of the geomagnetic field are acting exactly like that. And these are technically called field line resonances, not a big jump there. And these have been known about for a long time as well within the geomagnetic community, just kind of siloed there. And what was astounding to me, which we got into the GCI work, is it's also been known for a long time that one of the fundamental frequencies of Earth field line resonances, is 0.1 hertz. You might remember me referring to that frequency earlier. It's exactly the frequency of the coherent human heart rhythm. So the fundamental resonant frequency of Earth and us and our heart rhythms is the same, especially when we're in a coherent rhythm, feeling good. But even if we're not, it's still in the same frequency range, right, of the autonomic and cardiovascular systems. So these are huge magnetically speaking. So when you look at them out of the magnetometers, these are giant waves, kind of these waves that are going on, these field line resonances, and they got this fuzzy, noisy-looking envelope writing on them. So when you zero in and look at that, that's the Schumann resonances. So a good analogy for this is if you're ever at the beach, right, you see the big waves coming in that are associated with the tides and so on, the kinds that knock you over if you're not careful, right, and you're standing in them. Those are the powerful low-frequency waves in this context. And riding on top of those is a bunch of little ripple stuff, right? That's the Schumann resonances. Does that make sense?
Yeah, absolutely.
Yeah. But both are important and both overlap. So in other words, both our hearts and brains are oscillating at the same frequency as the primary rhythms of Earth in two different mechanisms. So if I may just rattle on a little bit here, back to science class again, and most of us got to play with tuning forks, right, to demonstrate the principle of resonance, but really it's resonant coupling that we're talking about. And what they didn't teach us back then, that it was absolutely true though, is tuning forks are highly coherent systems. If you don't have a coherent system, there's no way to have resonance, first of all, right? So Earth is a coherent system, and so are we, more or less, in this respect. So, but once that, you tap the one tuning fork and the other starts to magically vibrate with it, what you're showing there is resonant coupling, which shows you can transfer energy and information between two systems vibrating at the same frequency. Right? In the case of our tuning forks, it's air molecules that mediate the energy exchange, but in magnetic domain, you don't need the air molecules. And it's exactly back to our other cell phone analogy of how we can pick the cell phone conversation out of the air we want. You create the resonant coupling with the frequency of interest, and boom, there's the energy and information transfer. And so what this implies, right, I can see you almost asking me that question with your look, is that we're all coupled to and exchanging information with the Earth's fields all the time. Right, so, I mean, the fact that we're all embedded within the field of the Earth, nobody's going to debate that, right? Even if you're in the space shuttle, you're still within the envelope of the Earth's magnetic field. And if you don't like that, well, the Earth in its entire magnetic field is within the magnetic field of the sun. There's no escaping this. We're all embedded, hierarchy of embedded systems within fields, within fields, within fields. We just can't escape that. And there are another one of my mentors, Franz Hallberg, Some of you might, a lot of people don't know that name. Another one of my close friends who recently passed as well. For those of you who don't know the name, he's the guy who coined the term circadian rhythms in the late 40s. And Franz, by far, has done the most work in this space because it didn't take him long to start seeing that circadian rhythms were affected not just by day-night photon stuff, but also by magnetic fields. And hundreds of studies have been published on this. This is not a hypothesis. And most of this work shows that when the Earth's magnetic fields get disturbed, which doesn't happen that often, but a solar flare and it happens to hit the Earth and it slams the field and gets it just all disturbed, that there's a lot of health implications on that. I mean, the hospital admissions, for example, in elderly populations, especially for things like strokes and heart attacks and myocardial infarctions and so on, goes away. It's 8% increase, typically, of hospital admissions. It's not trivial. People don't sleep as well. Multiple studies showing that. And things like we're quicker to get irritated, right? And do silly things and get into car accidents. I mean, it goes on and on. It's a global effect.
I think I read about melatonin.
Melatonin is one of the things that a lot of hormones and things have been measured. So we're getting into the physiology now. But yes, absolutely. Melatonin is one, blood pressure, but rhythms, hormones, a lot of things that mediate that. So what our recent studies, which is really the first that I know of to do, is we've been looking at groups of people wearing these HRV recorders 24 hours a day in the ambulatory context for many, many days in a row, like months. One study we hopefully in our last round of reviewer feedback now that should be coming out in one of the Nature journals shortly, looked at a group over a 5-month period. So we just got a couple of studies that were just published on this other aspect. That was the surprise. So we were originally doing this work because HRV, I didn't say this explicitly, and I should here in this context, reflects the dynamics going on in our nervous system. And that's what that actually is. So it's a great tool to look at, are there nervous system changes that are associated with or driven by changes in the Earth's magnetic field, the time varying, these resonant frequencies in the Earth. So that was our original reason for doing these studies. And yes, they do, and there's highly significant effects. But the surprise came when we time synchronized the HRV data. This started from a small study of 10 people. Has now gone on to much larger studies. But these 10 people, to give background here, were located in various parts of the state of California. These are not people in a room together holding hands, meditating or some nonsense. They're going about their normal lives over a 30-day period, some in Southern California, some in Northern, some in Central. They don't necessarily even know each other. Some do, but not, doesn't really matter. Anyway, when we time synchronized their data, and they wore these recorders over 30 days, we expected that it would just all average out to a noisy flat line. I mean, if you think about it, we're measuring the time intervals between my heartbeats and your heartbeats, right? We're going about our lives in separate parts of the world. Should be no correlation there. And we took out circadian rhythm effects because that would obviously be a factor if we were both sleeping and waking at the same time in the same time zone. So that's all removed. And we were shocked when we saw the result of that analysis. It wasn't a noisy flat line. What we saw was that the rhythms, which we now call slow wave rhythms, a couple of important discoveries here, that there actually is this much slower frequency in heart rhythms than identified past the ULF band, first of all. And those were synchronized across the group. And we're like, how the heck can this be? And it should have been obvious but in hindsight, but it's one of our hypotheses, after all, in the global coherence work. But anyway, what we found was that they're synchronized because we're synchronizing to the rhythms in the Earth's field. So that became...
What is this frequency range that you're talking about?
Well, this is in the Fieldline resonance rhythms. It's the low-frequency rhythms that are especially important in our heart rhythms. But the slow wave rhythm we're talking about is over many hours to days. So you could see a sine wave kind of pattern of the group synchronization. That's like a 2-day rhythm.
Wow.
Yeah, that's what we said. I mean, I of course showed this to colleagues and things, and they did what you just did. Their mouth dropped open and said, wow, this is the most important data I've ever seen. Of course, this is 10 people, California, right? We said, okay, we got to verify this. So what the next step was, And that line of research was we had groups of 20 people in 5 countries. And the same countries we have our magnetometer sites in. So it's well over 100 people now doing the same thing. And so we've certainly verified this globally, and with the larger N, been able to identify subgroups within the bigger group. And I won't go into the details of that. We're getting ready to publish all that now. And another side aspect of that, we added some additional questions. And in fact, this is a paper I'm working on right now with some collaborators in Lithuania, was that in that big study, we had all the groups do one of the HeartMath techniques, which is a heart-focused meditation called a heart lock-in, where you really shift into a coherent state. I don't know if you're familiar with that or not. Yeah. For 15 minutes. Okay. And we were actually wanting to see if we could see global synchronization between people, just as a kind of a wacky thing to ask. Another surprise came out of this, and we haven't looked at that aspect yet. We will be. But what we saw was on the day that, for 15 minutes now, I'm talking about, that all the groups, and there was this one time that all the groups did a heart lock-in together at the same time. And we were able to organize that across all these crazy time zones. And what we see is that the synchronization between all the individuals and all the groups radically increased from that one 15-minute heart lock-in. And that actually had effects that lasted over 2 days. I mean, it's almost unbelievable. We're doing everything we can to disprove it right now, and haven't been successful. It seems to be a very real effect. And us just getting in a heart coherent state, deeply felt for 15 minutes, profoundly increased our synchronization to the rhythms of the earth, which I think is a very good thing, by the way. A lot of reasons now from multiple studies to suggest that the magnetic field of the earth literally acts as an energy source for us. And that being synchronized, we're part of the shared humanity field, would be a little bit more abstract reason there, but which I certainly believe to be true. So we're feeding the field. It's a long answer to your question, but
because one of the things that you guys have done in the past is research, and let me know what your time constraints are.
We're about lunchtime, so we can do another question, and then we'll wrap it up.
Well, the question is a little more esoteric, a little more into kind of fringe physics, if you will, is around scalar fields. And it's been proposed that the heart is a bidirectional scalar antenna.
Yeah, could be. I don't know. It's not
out of your domain.
Yeah, I mean, we had a guy who worked in our lab many years ago that was really into the scalar fields, and like where you reverse wind coils and all this stuff to create. And I think there's probably something to it. I mean, if you think of this idea that if you have one of the ways that I know that in the physics side of things, if you want to create these so-called solar, I don't really understand scalar fields. I'll be really upfront and honest here. But to produce them is you take 2 wires and you wire them together so that the 2 fields oppose each other, so that you have a net zero magnetic field radiated. Mm-hmm. But if you think of that as pressure, like if you were between 2 plates, if one of us got stuck between 2 very big plates that had equal pressure, maybe 1,000 pounds on each side, well, we'd be squashed. Right. I would not want to be in between those 2 plates, right? Yeah. Even though the net field is 0, the net pressure. So there's probably something to this that we're a small group and only focus on so many things here. Whether the heart acts as a scalar field, I have no idea. But it's certainly, I don't know that it could in the traditional context, because we have a measured magnetic field, right? As opposed to this, But thank God, I think. Because that's what I'm suggesting couples to the Earth's magnetic field through resonant principles.
Is that where you guys are going? We'd say the next 5 years is to keep kind of following this thread?
Well, we'll certainly keep following the thread of global interconnectivity, because one of our hypotheses is quite literally that the Earth's magnetic field is a type of biofield that we're all connected to and live within, and that we're all feeding that field. So there's more work to be done to sort out, can we prove that, and what are the mechanisms of it? And we're starting to get onto some things around that I won't go into here, and we're also launching, hopefully this year, it's called a Citizen Science Global Tree Monitoring Project. So you can monitor your own trees in your yard or whatever, because trees are another living system that are part of the field. So one of our hypotheses is it's similar to the random number generator networks that are out there and so on, that see a big effect when you have a mass-triggered human emotional event, something that triggers a lot of people feeling angry or compassionate, whatever, that you can measure that globally in a change in randomness in physical devices. Well, we suspect that we'll also be able to see that in living systems, like the electrical potentials of trees, for example. And there's other reasons we're doing that as well. But our main focus, just to wrap up here, is social coherence. So we're developing right now a new technology platform rather than the devices we have now, like Interbalance and M-Waves and so on, that measure your personal coherence, which are great, and it's a great training tool to be able to do that at the group level. So we can facilitate groups getting more harmonious and in sync, and then new trainings for that technology that really help us give new tools and techniques for getting together, getting along better in groups, and literally getting more physiologically synchronized, which is an important factor in group performance and harmony.
Yeah. Well, thank you, Dr. McCraty.
You're welcome.
Looks like people are trying to sit down and enjoy their lunch here, so we'll sign off.